Hello everyone, welcome to the BDM channel, Motor Selection Series. I'm Bill. Today, we will study the third lesson of our special series, Stepper Motor Typical Characteristics and Applications. Why have we dedicated a whole lesson just to discussing typical characteristics and applications? Because this topic, it is extremely important. It directly relates to whether during later use, we can leverage its strengths and avoid its weaknesses to make a reasonable selection. After all, stepper motors are relatively inexpensive. Generally, a full set costs only a few hundred RMB. So, relatively speaking, if compared to servo motors, the cost of a machine using all servo motors could be much higher than one using a mix of servos and steppers. As you can see, the automatic screw-driving machine on the left uses 6 stepper motors. This way, the cost is immediately reduced. If it used 6 servos instead, the cost would be higher. Well, when we are designing, it's important to know stepper motors have these key features. Let's study them together, alright? First, similar to servo motor control. Generally speaking, a stepper motor requires a dedicated driver to send pulses for its operation. The angular or linear displacement is proportional to the number of electrical pulses. One pulse turns one step angle. By controlling the pulse frequency, we can control the motor's rotational speed. By controlling the pulse sequence, we can change its direction of rotation. So, this means that in many non-critical applications, or where speed is not very high, or precision is not critical, it can often be used to replace a servo motor. However, for applications requiring torque control, a stepper motor cannot replace a servo because it does not have a torque control mode. Okay, second, during its operation, a surface temperature of 80–90 degrees Celsius is considered normal. If the temperature gets too high, it can easily cause torque drop or lost steps. Therefore, stepper motors are not suitable for continuous running to prevent excessive temperature. Actually, in which scenario did I gain this experience? For example, on a conveyor sorting line we previously built, its sorting diverter used a stepper motor. Now, this stepper motor was from Lisai, and, at that time, it was running non-stop. As soon as it was powered on, it ran continuously. It wasn't like our modules, where the motor might start and stop frequently. After running for several hours, it would stall and cause an alarm. Why was this? It was due to continuous operation causing overheating. So, this means that, for applications requiring continuous operation, we can use 2 methods to solve it. First, change the motor to a servo, right? Second, for instance, suppose a size 42 motor would suffice. We could instead choose a size 86. Why is that? Because in this case, even if its temperature rises and torque decreases, it can still drive the load effectively. So, this is one method to overcome the torque drop from high temperature, which causes stalling or alarms. Okay, third, stepper motors, when running at low speeds, have significant vibration and noise. At this point, it's also related to the load and the driver's performance. A common mitigation method is to subdivide the step angle, which is our step angle, also called step angle. Perform micro-stepping. For example, 5-phase motors have lower vibration and noise than 2-phase ones, but you can also use micro-stepping. Or, if the speed is sufficient, we can add a gearbox. Adding a gearbox means for a stepper motor, using it with a gearbox effectively subdivides the step angle in a way. Isn't that so? Of course, you can also, if cost is not a concern, switch to using a servo motor. That's also fine. Okay, fourth, starting requires a gradual acceleration process. That is, for our stepper motor, if, at higher rotational speeds, the output torque is smaller. This is inherent. Therefore, when starting at high speed, stepper motors are prone to losing steps. Actually, relatively speaking, stopping from a high speed state can cause overshoot, losing precision, or losing angular control. Generally, when we use them in design, first, the starting torque should be lower, and second, at high speeds, it's not suitable to use steppers. Generally, for stepper motors, controlling an indexing table, or controlling a robotic arm, the speed should not be too high. If too high, it loses steps. This is essentially a case of dropping torque. We just drew a torque speed curve, isn't that right? Because, at high speeds, it is prone to losing steps. This is something we need to pay attention to. At high rotational speeds, its torque drops sharply. This can cause lost steps. You must remember this point. That's why I repeated it twice. Okay. Fifth, for general positioning applications, considering cost, we generally choose stepper motors, but it's undeniable that, for some high-precision applications, requiring feedback, requiring rapid acceleration and deceleration, requiring fast positioning, or requiring torque control applications, we would still choose servo motors because its overall performance is better than steppers in these aspects. Therefore, this fifth point needs special attention. That means we must analyze based on the specific situation and select the appropriate motor type accordingly. So, to summarize today's content, we covered several stepper motor characteristics. First, it can achieve speed control and position control. Second, temperature increase causes a drop in torque. When selecting, we must consider the torque speed curve and the effect of temperature. Third, stepper motors have vibration and noise at low speed. Our solutions are micro-stepping or changing the motor, right? Using 5-phase instead of 2 or 3-phase, or we can add a gearbox to help avoid the noisy resonance speed range, or of course, switch to a servo motor. However, when we are designing, we should avoid high-speed operation or starting, as it can cause lost steps or overshoot. So, this point also needs attention. Generally, for high precision or torque control applications, we use servo motors to replace steppers. So, these are the typical characteristics of stepper motors and their application considerations. Well then, I have provided a summary for you here. You later during your studies, please note this down in your notebooks. And during our design process, focus on analyzing these points to choose the appropriate motor type. That's all for today on stepper motor, typical characteristics, and applications. We'll see you in the next lesson.